Hey there, math fans. I'm Dr. Andy Lovelace. Buckle up here. We're going to talk about Fibonacci numbers and how we can use Taylor series to analyze them. If you don't know me, I've taught at the University of Washington for 20 years, and I'm making videos like this to try to show students some interesting things beyond our basic calculus course and try to tell them in some sort of basic way. Please like and subscribe and give me some feedback if things like this are interesting to you. The Fibonacci numbers are these. There's a lot you can find on this online, I'm sure, where you start with 0 and 1 and you add the previous two. This came up, there's historical significance in studying populations of bunnies, actually, is the first writing about this. I've labeled those in this graph you can see at the right. So here they are as we go over. At 1 month, there's one bunny at 2 months. This was a model that basically said it takes a month before they can reproduce, and then each one, and you get this really fast growth. Those are all whole numbers. This is an unusual thing you can do with generating functions, is it takes you a way to work with whole number sequences and analyze them using calculus. And usually calculus is not very good at dealing with whole number things. Anyways, here's this formula. This formula is extremely accurate. So if this is the 1, 2, 3, 4, 5, 6, 7, 8th Taylor, I keep saying Taylor polynomial. What a fool this guy is. Okay, so 1 plus this. If this is the 8th Fibonacci number, you can put an 8 right here, and this is basically it. It is extremely close to that value. Here, I'll graph it for you. That blue line is what you get if you call this x. It's like almost a perfect fit. What in the world? Why would you get these square roots of 5? Okay, let's get rid of that graph and let's dig into it. So in the end, this is where the part that's for my students, we are going to use this. The end of the little derivation, which is what I will finish in this video, uses this. The geometric series, something my students have been plugging into a lot. Kind of sick of plugging into it. We've been talking about various things. We're going to plug something in there, and it's going to involve this number. How? All right, so that's the setup. So I'm going to say a few just quick general things, and then I'll do the derivation. Okay, so Fibonacci was the 1200s. My little bit of reading of the history, I've read this off and on over the years, is that really not very much is known. There's writings. He had a book. A lot of that didn't survive. So what we have is recreations of it, things that at some point somebody had taken down some chapters. That's what I read. He did study bunny populations. This is the recreation of what he had. Studied the sequence. So he's kind of the first formal analysis of this. And there's been all sorts of things. People claim to see this in nature. There's things about, these are Wikipedia pictures. Things about if you make a square where the side lengths are 1 and then another one with 1 and 2, you get this thing. If you connect with the intersections, you get this golden spiral. All right. Some people say it's the most pleasing ratio. It really the golden ratio comes about of this thing of, what if I want the ratio of the sum of two lengths equal to the ratio with one of the sides be the same as the ratio between the sides in the following way. That leads to a quadratic, and you can solve, and you get this so-called golden ratio, about 1.6. Now, there's been studies if that is the most pleasing ratio, like if you build a picture that is 1 by 1.6, is it the most pleasing? There's been arguments about it. There's arguments about whether famous landmarks have that ratio. Some other just fun things about this, the golden ratio is given by this. So if you've never seen infinite square roots or infinite sums, there's a cool thing about them. If they converge, you basically say, well, this is x, and this is the square root of 1 plus itself. I remember as a student just like playing around with this. And then you can square both sides, solve, and you get this quadratic, which you can solve, and one of the roots is that. All right, let's get to the derivation. So keep that golden ratio handy. We'll need it in a second. It's the solution to this equation. One of the solutions to this equation. Okay, here we go. So here's that part that has to do more for my calculus students. Imagine you take the Fibonacci numbers and you lay them, as I like to say, on our clothesline. Now I'm not going to include factorials as if they're derivatives. I'm just going to pretend those are the coefficients in some power series. How in the world can that be helpful? It's like we're just laying out some numbers there. Well, the interesting thing is, because we have this little recurrence, this thing that says the second one is equal to the first one plus the 0, and the third one is equal to the previous 2, we can manipulate our series, essentially in terms of itself, to say something about it. Okay, so here we go. So let's play this game and see what happens. So if you multiply everything by x, it's surprising that this would help, and I've shifted things so everything kind of lines up. Here's what we see. So if you multiply all of it by x, this is going to become f sub 0x. This is x squared. And I'm writing without the sigma notation just so we can really see what's going on. If you multiply everything by x squared, you shift it 2 spots. There we go. And then the observation is this. This equals the sum of those two. And since our coefficients are equal, they essentially are equal at that spot. This equals the sum of those two. And that happens forever. So we can say something here. Unfortunately, there's this little stuff hanging out in front. But we can basically say that this plus this, those two, add up to that with a few adjustments. So let's talk about those adjustments. This is actually 0, so that doesn't mess anything up, but this does. So I need to get rid of that x. So it goes like this. It says, we can actually say something. We can say if you take the function and subtract x, then you're going to get this thing up here. And that's the same as the sum of the other two. And from that you can rearrange. It's really a clever little bit of solving. So from this we can actually find the function. So surprisingly, there is a function for the Fibonacci. We call that a generating function. But it's a typical function, like it's a function we can analyze. That's the key bit. Now we can use our full calculus toolbox. What do I mean by that? We have a way to give the Taylor series for that. We have a way to give a power series for that. And the way is to break it up into partial fractions so that we have two things that look like this, and then plug those in the geometric series, and we have it. So it's a lovely little, very different application than my students are seeing in my course, so that's why I wanted to do this at some point, and I hope you're finding it interesting. Okay, so I'm not going to show some of the pieces are a little messy here, but ultimately if you solve this, and you do your negative b plus or minus square root, you get this thing. You get that square root of 5, you get over 2. There's some comments to be made here about how you would factor, but I would like to factor in a way so there's a 1 here. And so there's a comment of, we're going to factor this using the roots, but we're going to do it in a clever way. You could have to verify that those are the same, but that's it. Once we do that, then we can think in terms of partial fractions and try to decompose it. Apologies if I'm going too quick. I'm just trying to get this here. So here we have our roots. That's the alpha and the beta. One of them is the golden ratio. One of them is -1 over the golden ratio. These numbers a and b you can solve for. They end up being 1 over the square root of 5 and -1 over the square root of 5. That's the partial fraction trickaroo. At that point, though, we've got it. So our final answer is going to be 1 over the square root of 5. And then we have these two geometric series. And we know the game we play. We can give the Taylor series for those. The sum from k equals 0 to infinity, alpha to the k, x to the k. So this is for my Calculus 3 students who are doing this exact thing. There's the moment where we're doing that. Then we can do all the same stuff. We can put these together, and that gives us the following. So I find that pretty incredible. This is a good example of taking, a sequence of whole numbers, realizing that you can represent it in a way that involves a function, and then you can use the full weight of the calculus we've been using. But that means that this right here is the same as this. And that's how we get this explicit formula. So you might say, well, that's a little different than what you said before. You said it was an approximate formula. I lied slightly. There is a precise formula. This is it. But this number is smaller than 1. It's basically 1 over 1.6. When you raise that to a power, it gets really small fast, like 0.00 whatever. So if you take this, subtract something extremely small, and divide, this pretty much rounds to your value is almost exact. And it's going to get closer and closer the bigger n gets. But this is an exact formula. I find that kind of almost disturbing that when you look at that, if you plug in a whole number here, this thing will spit out a whole number. It'll spit out the Fibonacci numbers. All right, that's just a little bit of a snapshot of a very different way we use power series as a tool to connect calculus with studying a sequence. All right, let me know if you find that interesting.